Hello everyone, welcome to all in this lecture. So in this lecture, I am going to discuss design of mat foundation. So mat foundation is basically a large slab supporting a number of columns and walls under the entire structure. We go for the design of mat foundation where the soil pressure is low, where the number of columns and walls are close to each other, where individual footings are overlapping with each other. So in all the cases, we can go for the design of mat foundation. Mat foundation is also useful to reduce the differential settlement, and we can also use the mat foundation where the soil is non-homogeneous type. So there are various type of mat foundation, and there are various method to design the mat foundation. So those are rigid beam method, simplified elastic method, non-linear elastic method. So in this lecture, I will discuss rigid beam method. Rigid beam method. So what is rigid beam method? In rigid beam method, we take the assumption that a raft or mat is infinitely rigid and the pressure distribution will be linear. What is the assumption? Assumption is raft is infinitely rigid and the pressure distribution is linear under the base of this raft. Okay, so this assumption is valid when the raft or mat is resting on the soft clay. If the mat or raft foundation is not resting on the soft clay, so this assumption will be not valid. So for that cases, we can go for the other method. We can go for the elastic method. So in this lecture, I'm going to discuss the rigid beam method. It means we have taken the assumption that raft is infinitely rigid and the pressure distribution will be linear. So in this figure, you can see there is a raft foundation which supports 9 loads, which are supporting 9 loads Q1, Q2, Q3, Q4. Their name is given up to Q9. Their dimension is given of B into L. So raft is in a rectangular shape, so centroid will be here. This will be the centroid because we know the centroid of this rectangular shape that will be at a distance of B by 2 and L by 2 from the edges. Okay, so there are various procedures that we can follow to calculate or to design the raft foundation. So first we will calculate the line of action of all the acting loads on the raft. So in this figure you can see, suppose the total loads Q, total loads is acting here, and this total load is Q. We can write the summation of all 9 loads Q1 plus Q2 plus Q9. This is summation of all 9 loads. Okay, so we'll find the position. So how we can find? We can first calculate X bar, then we can calculate Y bar. So how we can calculate? So there is a formula I'm writing, and also we can calculate by using the moment theory or by applying a moment from the edge. So we can write this formula also. So I'm writing directly. So X bar will be Q1 X1, Q2 X2, Q3 X3, Q9 X9 divided by Q. Q is the summation of all 9 loads, where the X1 is the distance from the edge, X1, this is X2, this is X3, right? Similarly, this will be X4, X5, X6. Now we can calculate X bar, so we can calculate also EX. This is eccentricity in X direction. So what will be the EX? So see this distance from here to here, that is B by 2. So we can calculate X bar minus B by 2. Right? Similarly, we can calculate EY. So we can write first, we can calculate Y bar. Q1, Y1, Q2, Y2, Q9, Y9 divided by Q, summation of all 9 nodes. So once we have the Y bar, we can calculate, got this, we can calculate EY, the centricity in Y direction. So this length is L by 2. So we can calculate EY, that will be the Y bar minus L by 2. Okay, and we will see this sign convention also. If the load is acting is above the x-axis, so that will be positive. Ey will be positive. If y is acting below the x-axis, so it means Ey will be negative. Okay, similarly we can do for Ex. If the load is acting right side of the y-axis, then Ex will be positive. And if this resultant load acting on this left side of this y-axis, means Ex will be negative. So we have to see, we have to check the sign convention also. Now we can calculate the pressure distribution, contact pressure distribution using this relation. So if the loads, the resultant load are coincide with the centroid, so in that case you will see x bar will be P by 2 and y bar will be L by 2. Okay, and in this case we will see the Ex and Ey will be 0. Both will be 0. Okay, so the contact pressure distribution you can get Q by A, where the Q is the total resultant load and A is the area, that is B into L. But if there is a eccentricity Ex and Ey in the x and y direction, so we can use this formula, and this formula is came from direct stress. This is the bending and stress, so we can write direct stress Q by A plus minus M by Z. M by Z we can write P K into E divided by I into Y. So if you are working in x direction, y direction, then you can write Kx and Ey. Okay. So in this equation, Ex and Ey put with the sign convention. And what is the Iyy? Iyy is the moment of inertia along the y axis. Ixx is the moment of inertia about the x-axis. This is very important. This, you can see this figure, origin is here. X-axis is this, y-axis is this. The origin is here. And origin is coincide with the centroid of this raft. So directly we can write Iyy and Ixy, xx, Iyy, Ixx. If suppose this origin is somewhere here, so we have to calculate the moment of inertia about the centroid of this raft. So this both moment of inertia, it should be at the centroid, of the raft. Okay. Okay, and what will be the value? So I'm writing here. See, this is P L. Okay, this is the x, this is y. So somewhere here load is here. So this is the Ey. Here working in a y direction. So we'll take the moment of inertia about xx. So we can write the Ixx will be B dq by 12. So B LQ by 12. And Iyy will be L BQ by 12. So this thing you have to remember. Now, we will divide this whole the raft in the number of strips or number of bands in x direction and y direction. So that you can see in the figure, we have divided number of strips. So this is 1, this is 2, 3, 4 strip in a y direction. We divided in a So the now we can work on the for the strip 1. So strip 1 dimension is, so this is the strip 1. Their dimension is B1 into B. Okay, and 3 loads are acting Q1, Q2, Q3. Okay, so now we can calculate the average load. Average load on the strip. On the strip means the strip 1. Here, average load on the strip first or 1. So that will be the half into downward load plus half into upward force. Okay, so downward load, what are the downward loads here in this for on the strip 1? That is Q1, Q2, Q3. Okay, and what are the upward force? So upward force is whatever the pressure is acting in upward direction. So that we are assuming that is QAV. So suppose QAV is acting on this below of the strip 1 in the whole area of this QAB. So what will be the total force? That will be, this is the pressure into area. What is the area of the strip 1? B1 into B. So that I have written here. Okay, so we can calculate the average load on the strip 1. So once we have the average load, then we can calculate modified average soil pressure. So whatever the total average load divided by the total area of the strip 1. So total load is coming, or we can say average load on the strip 1 is coming QAV. So we can divide by the area, that is area of the strip 1, that is B1 into B. So we can calculate modified average soil pressure. Now we can calculate column load modification factor F, column load modification factor. So that will be, we can calculate by using this relation where the QAB is average load on the strip 1. See, from the step 4, we are working on the first strip. Okay, we are not working on the whole raft. We are working only on the first strip. Okay, strip 1. So we'll calculate column load modification factor for the strip 1. So that will be QAV divided by Q1 plus Q2 plus Q3. Now we can calculate modified column loads. Now we can calculate modified column loads, and that will be the F into Q1. So every modification, every loads we will multiply with the column load modification factor. So we can get modified column loads. So once we have the modified column loads, we have the modified soil average soil pressure. We have these two value. So we can go for the draw the shear force diagram on bending moment diagram. So for the draw of bending moment diagram, we have to know this value Q bar AB, and we have to know this value QF1, QF2, and QF3. So once we have these two values, we can go for the drawing of this shear force diagram and bending moment diagram. So I will discuss one numerical problem so that we can understand in a proper way. Okay, so this is the one question. The plan of a mat foundation with the 9 columns is shown in the figure. Assuming the mat is rigid, determine the soil pressure distribution. All the columns are a size of 0.6 meter into 0.6 meter. So determine the soil pressure distribution, and then we can go for the drawing the shear force diagram and bending moment diagram. Okay, for the strip 1. So I will show for the strip 1. You can go for the strip 2, strip 2, strip 3, strip 4 also. Okay, I will show for only first strip. Okay, so first we will calculate the total resultant loads, total line of action of total resultant loads, so that we can calculate. See, centroid is here because this shape of raft is rectangular. So centroid is here. This is the centroid. So we'll calculate the X bar. So for the X bar, we can calculate this. We can write the formula Q1 X1 plus Q9 into X9 divided by Q. Yeah, total loads we can write Q1, Q2 plus Q9. Okay, now we can write the value. So Q1, and we will write like this, because this the load Q1, here is the Q4 and this load. So this will be all at the same distance. So we can write like this, 500 plus 1500 plus 400. So this will all be at a distance. So what is the distance of this? So this will be, you can see the dimension of this 0.6. So this will be 0.3. So from here, x1 will be 0.3. Here x4 will be 0.3. Here also x7 will be 0.3. So we can write 0.3 plus. Now we'll calculate for this 3 load. Okay, so we can write 600 plus 2000 plus 500, and these all are at a distance of this 12.6 total. So this distance will be 6.3. We can write 6.3 plus. Now we can calculate for all 3 loads. So that is 400 plus 1200 plus 300, and distance of these loads. So that will be 12.3. So here up to total is 12.6. So this will be 0.3. So we can write this will be 12.3. Okay, so into 12.3 divide by total loads, that is 500 plus 600 plus 300. This is Q9. So that we get x bar 5.89 meter. So 5.89 meter, it means somewhere here. Q is mentioned, this is here. So now we can calculate Ex. So that is x bar minus b by 2. Means x bar is okay, x bar is 5.89 minus b by 2. What is b? 12.6. So we get 0.41 negative meter. So negative means it is load is acting left side of this y-axis. Okay. Now we can calculate, similarly we can calculate for y bar. So that will, can I write directly? First let me write this: y1 q1, y2 q2, q9 7 y9 divided by total load. Okay, so we can write, see on the now I'm calculating the y bar. So with all three these loads will be on the same distance, these 3 load. So I will write together 500 plus 600 plus 400, and what will be the distance from this? That is 0.3 plus. Now this 3 load, that is 1500, 2000 plus 1200 on our distance from here to 8.3 plus 400, 500 plus 300 into 16.3 divided by total load. Okay, so that we get y bar value is 7.98. 7.98 meter. You can calculate also. So now we can calculate E. Okay, so now we can calculate EY. So that is y bar minus L by 2. So what is y bar? 7.98 minus L by 2, that is 16.6 divided by 2. So it is coming 0.32 negative. In negative, it means it will lie below the x-axis. Okay. So you can see in this figure also. Okay. So now we have the EX and EY. So we can calculate. So now we can calculate the pressure distribution. Okay. So we can apply the formula that mentioned in the previous slide. QA total divided by Q into plus minus Q into EX divided by IYY into X plus minus Q into EY divided by IXX into Y, right? So just put the value. So whatever the total loads, so summation of the total loads, we can get this 5, 6, this summation of all loads, we can get this 74 kilonewton, 2400 kilonewton, right? So we can write 7400 divided by what is the area? That is 12.6 into 16.6. Okay, and what we will write? Plus minus. See, in this case, what we will write? Plus or minus. So, and in the X here, they say intercity EX EY, we will apply according to the sign convention. So we have seen that EX and EY both are negative. So we directly we can write minus. So that will be the minus into Q, that is 7400 into what is EX. So EX is 0.41 into X. Don't put the value of X, let it be unknown. Okay. So now moment of inertia. So 1 by 12 into IYY. So that will be B dq by 12. So what will be the B? So B will be 16.6 into 12.6 Q minus 7400 into what is the EY? So that is 0.32 into Y. Let it be Y unknown. So 1 by 12 into 16.6 to the whole Q and then 12.6. So we can calculate, and after calculating we can get this result: 35.4 minus 1.1x minus 0.5 y. Okay, so this is the relation we got. So if we can calculate the pressure distribution or the pressure at any point within this raft by putting the value of x and y according to their coordinate. Okay, by putting their sign convention also. So now let's assume we divide the this raft in the number of strips. So I'm dividing this strip. I'm taking, this is the first one, and I will work on this strip 1. So now the dimension of this strip is 12.6 into this width. So center to center up to here, this will be the 4 meter, and here, so this width will be total 4.3. Okay, so now we can calculate the Q pressure at a point A. Pressure at a point A. Okay, so now if we are calculating the pressure at a point A, so what will be the X and Y? So both will be negative. 30.4 into minus 1.1. What will be the X? And from the here, this is the origin. So X will be, this is the 6 meter. So we are calculating here. So 6.3. So minus here 6.3. 6.3. We are point A here. So it will be distance 6.3, right? Okay, now minus 0.5 into Y. What will be the Y of this point? So it will be minus 8.3. Okay, so that we get 46.4 kilonewton per meter square. Similarly, we can calculate at a point B, 35.4 minus 1.1. What is the x coordinate of point B? So that is positive 6.3 minus 0.5 into what is the y coordinate of B? So minus 8.3. So we get 32.6 kilonewton per meter. Now we can calculate at a point here. Suppose this point is given name. Suppose this point is E. So we can calculate at a point E. So that will be 35.4 minus 1.1 into what will be the x coordinate of this? Will be 0, because this is on the y-axis. So x coordinate will be 0. Minus 0.5 into what is the y coordinate? So that is minus 8.3. So it will come 39.55. Now we'll take the average at a point A, E, and B. So we'll take the average. So average pressure, average contact pressure, we can say average contact pressure will be divided by 3. So will be QA plus QE plus QB. So that will come around 39.5 kilonewton per meter square. So now we have the average, but we have to calculate modified soil average, modified average pressure. Modified soil pressure, yeah, we can say modified average soil pressure. So this is the average soil pressure or average contact pressure, we can say, but this is not modified. So to calculate the modified, we have to calculate the total loads or average loads, not total loads, average load on the strip 1. So let's go to calculate average load. Average load on the strip 1. So that is half QAV half into Q1 plus Q2 plus Q3 plus small QAB into B1 into B. Okay, so we can calculate half into what is Q1? 500, Q2 600 plus Q3 400 plus 39.5 into what is B1? 4.3. What is B? 12.6. So we can get this value, total load 1820 kilonewton. You can check also. So now once we have the QAB, we can calculate modified soil average QAB bar. So that is QAV divided by B1B. So 1820 divided by 4.3 into 12.6. We get this value 33.6 kilonewton per meter square. 33.6. that is Q bar AB. Q bar AB. Okay, now we can calculate F. So that is QAV divided by Q1, Q2, Q3. So we have 1820 divided by Q1, that is 500, Q2 600 plus Q3 400. So that we get F, that is 1.21. 1.21. So now we can calculate FQ1, that is 1.21 into 500. So what we get? We get 605 kilonewton. By multiplying, we can get kilonewton. Similarly, we can calculate FQ2, FQ2, that is 1.21 into 600. So that we can get 726. Similarly, FQ3, we can get 484 kilonewton. Okay, so now we have this FQ1, FQ2, FQ3, and we have the modified soil average. So now we can calculate, or we can draw the shear force diagram and bending moment diagram. So first, for drawing the shear force diagram and bending moment diagram, draw the line diagram. So this is the line diagram I'm showing here. So this is the upward pressure, and here this is this FQ3, FQ2, FQ1, and this is the Q bar AV. So this is 33.6 kilonewton per meter square. So this is the modified. So we can calculate UDL. So what is the B1? So for UDL we can write Q bar AB into B1. That is 33.6 into 4.3. So we got 144.5 kilonewton per meter. That I've written here. Okay. Now we can go for the drawing this shear force diagram. So for shear force diagram, we can take the sign convention. Either we can go for from the left side or right side. So I'm taking the sign convention. Suppose this is the sign convention. If you are working from the left side, from the right side, so downward force will be positive and upward force will be negative. So at point here, this will be the 0. So this is the UDL. So this is the in upward direction. So this will be in the negative. Okay. So we can write shear force at, I'm giving the name. So the end point is A, just below the load B, here, somewhere here, where the shear force will be 0, suppose. So C, here D, somewhere here shear force will be 0. So E, this point is F, and the end point is G. Okay. So now I'm going to calculate shear force at a B. Shear force at a B. Just right side of the point B. Okay. So we are coming from the left, so we can write negative, because this is the upward pressure, 144.5 into 0.3, because this distance is 0.3. Okay, so that we get 43 minus 43.4 kilonewton. I'm writing overall. Okay, so this will be somewhere here, and this will be linearly vary, but this is UDL, so this will vary as a linear, so it will be like this, 43.4. Now there is a sudden change because this is a concentrated load, so that is in downward direction, is positive. So by adding a 484, you will see there is an addition of Okay, so you will see that this will be the 440.6 kilonewton. Now again, there is a real load, so it will vary. So we will calculate shear force. So we can calculate shear force at this point, x-axis. So we can see where the shear force is 0. So let's calculate x, and this distance is from the left side is x. Okay, so we can calculate shear force on x-axis will be minus 144.5 into x plus 484 will be 0. Okay, so we can calculate x so that we can get 3.35 meter. It means shear force here, somewhere here will be 0. Somewhere here will be 0. And the distance of from this point to here is 3.35 meter. Okay, now we can calculate the shear force at a point D. So shear force at a point, put the x is equal to 6.3. 6.3. We'll get shear force at point D minus 144.5 into 6.3 plus 484. Okay, so we'll get the value, and that is 420.6 kilonewton, and that is negative. So here somewhere 4 minus 420.6 kilonewton. This is positive, this is negative, this is negative. Okay, and they will get sudden change here, so that will be the concentrated load. So it will be 305.4 kilonewton. Okay, now again you will see there is a variation in the change. So by doing this we can calculate so it will be like this. Okay, you can calculate also. So we can write shear force at what point shear force will be 0. So I'm taking the x-axis here. So x-axis shear force at x-axis. So 1 minus 144.5 into x plus 726 plus 484. So put the value of 0. So we'll get the x, and that will be that I'm calculating from the right side. So we'll calculate from the left side. You will get this value. This value will come that 4.18 meter. Okay, 4.18 meter. So we'll get this value, that is 12.6 minus 4.18. Okay, we'll get this value. Okay, so now we can calculate, put the value of x is equal to, put the value of x is equal to 12.3. So we'll reach here. So we can calculate shear force at F, so that we can get shear force. So minus 144.5 into 12.3 plus 726 plus 484. So we will get there is a minus 561.6 kilonewton. So there is value 561.6 kilonewton negative. So again there is, you will get some change. So here you can get 53.4 kilonewton. because there is concentrated load, and finally it will reach to 0. So we'll see this bending moment will be here, will be maximum at a point 4.18 from the left, and here will be the maximum at this point also. So maximum will be here, okay? For the shear force is 0 here. Okay, so now bending shear force diagram is ready. You can see at what location shear force is 0, at what location shear force is maximum or minimum.